In this session, we are going to discuss about frequency domain sampling. So, let us consider signal, discrete time signal x of n. For that discrete time signal, if you calculate Fourier transform of the signal, we can write as per the definition of Fourier transform, we can write x of omega equal to summation over the limits minus infinity to plus infinity x of n multiplied by e to the power minus j omega n. So represent it as a equation number 1. Here in this equation, x of n indicates discrete time signal. This indicates discrete time signal, whereas x of omega indicates whereas omega indicates frequency component of the signal. Okay, x of n indicates discrete time signal, whereas omega indicates frequency component. So one point we have to note here, that is omega is the continuous function from, it is a continuous function from 0 to 2 pi, where omega is the continuous function from 0 to 2 pi. This means even though x of n is discrete time signal, its spectrum is what? X of omega is the spectrum. It means x of n is discrete time signal, even though its spectrum x of omega is continuous. It is discrete in nature, but the spectrum is in continuous nature. So such continuous function cannot be, it is continuous. Such continuous function cannot be evaluated on digital processor. On digital processor, only discrete signals can be evaluated. So this point we have to remember. Here in this case, it is a discrete time signal. X of n is a discrete time signal, but we are getting its spectrum in continuous form. So in order to evaluate signals on the uh, digital processor evaluates only discrete time signals. So in order to overcome this problem, the spectrum x of omega is sampled uniformly. So x of omega is periodic with period 2 pi. It is periodic with period 2 pi. Now we have to sample this spectrum uniformly. So hence n samples I will take between 0 to 2 pi. So I'm going to sample this spectrum by n samples. So I'm going to divide the spectrum by n samples. Hence, the spacing between successive samples, spacing between successive samples, spacing between successive samples will be 2 pi by n. It means if I divide the spectrum 0 to 2 pi by n samples, so 2 pi by n, so the successive samples, the spacing, the distance between successive samples becomes 2 pi by n. So I am going to represent in standard format. Let us take omega equal to 2 pi by n into k, where k is the integer value. The value of k varies from 0, 1, 2, 3, so on n minus 1. Why it is varies from 0 to n minus 1? Because we sample the spectrum by n samples. Because of that reason, this is the integer value. K is an integer value. It varies from 0 to n minus 1. If you substitute 0, first point is 0. If you substitute 1, we are getting 2 pi by n. Next one, 2 pi by 4 pi by n, like that. We'll take one examples. We'll get the clear idea. So the above equation 1 we can rewrite with the help of omega equal to 2 pi by n into k. Hence equation 1 becomes wherever omega is there, substitute omega equal to 2 pi by n into k. Hence equation 1 becomes, we can write, that is x of 2 pi by n into k is equal to summation n equal to minus infinity to plus infinity x of n e to the power minus j 2 pi by n into k into n. This is omega value. So I will represent it as a equation number 2. So we will take one example. If I consider n equal to 8, if I divide the spectrum by n samples, okay, what happens? So it means for this example I am going to divide the spectrum 0 to pi by 8 samples. So this is a spectrum, starting point is 0 and end is 2 pi. If I divide this spectrum of length 2 pi by 8 samples, then what will be the first sample? In this case, 2 pi by n into k. 2 pi by 8. 2 pi by 8 means it becomes pi by 4. Substitute k equal to 0 means 0. Okay. Here I am going to write 2 pi by 8 into k. This becomes 2 pi by 8 into k. So this is, we are going to substitute the values of, or we can write this is equal to pi by 4 into k. Keep on substituting the value of k from 0 to n minus 1 means we can write 0 to n is 8 as per this example, 0 to 7. 0 to 7 as per this example, and the value of k varies from 0 to 7. If k equal to 0, first sample 0. If k equal to 1, first sample what we are getting, pi by 4. If k equal to 2, it becomes pi by 2. If k equal to 3, it becomes 3 pi by 4. If k equal to 4, it becomes pi. If k equal to 5, it becomes 5 pi by 4. If k equal to 6, it becomes 3 pi by 2. If k equal to 7, it becomes 7 pi by 4. If k equal to 8, it becomes 2 pi. Hence, so we divided the spectrum by, for an example, by 8 samples. So we got these many samples. How many samples we got? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 8 samples we got. So likewise, we have to sample. So spectrum, continuous spectrum, we sample by 8 samples. This is the case. This figure shows that frequency domain sampling of the spectrum x of omega. This figure shows frequency domain sampling of the spectrum x omega. So here, thus k, the value of k is an index. The value of k is an index. The value of k is an index for these samples, and x of omega is calculated only at discrete values. Consider n equal to 8 samples are taken over the period of 2 pi. Hence, x of omega will be calculated omega equal to 0, omega equal to pi by 4, pi by 2, 3 pi by 4, pi, 5 pi by 4, 3 pi by 2, 7 pi by 4, like that. These samples are addressed by k equal to what? K equal to 0 to 7 samples. So next is to determine the minimum value of n. See, in this case n is there, but we have to calculate minimum value. So this we discussed with an example of 8, but practically speaking we have to calculate what will be the value of n. So next step is determine the value of minimum value of n. Determine minimum value of Okay, how to determine? Say in equation 2, this is equation 2. In equation 2, note that n varies from, the value of n varies from minus infinity to plus infinity, correct? The value of n varies from minus infinity to plus infinity. Let us divide this summation term into individual summation terms. It means there are so many summation terms. How many summation terms are there? Minus infinity to plus infinity. These many summation terms are there. I'm going to divide these summation terms. But one more point we have to remember, in each summation term, these many calculations we are performing. Once again, I'll repeat, there are how many summation terms are there? Minus infinity to plus infinity, because the value of n varies from minus infinity to plus infinity. So many summation terms are there. In each summation term, we are performing uh, this calculation, x of n multiplied by e to the power minus j 2 pi by n into k into n. One more point we have to remember here, the value of k varies from 0 to n minus 1. It means here two indexes we are getting, n and k. N acts as an outer index, k acts as an inner index. N acts as an outer index, k acts as an inner index. So n varies from minus infinity to plus infinity, k varies from 0 to n minus 1. For each value of summation term, for each value of n, it may be n equal to minus 10, n equal to minus 8, n equal to 10, n equal to 100, n equal to 1000, whatever it may be. For each value of n, we have to perform this calculation by varying the value of k equal to 0 to n minus 1. Generally speaking, for each summation term, n calculation, each summation carries n calculations because index k is there. So I am going to divide this summation term as x of 2 pi by n into k is equal to LHS. How many summation terms are there? Minus infinity to plus infinity. Summation, summation, plus summation, plus summation, plus so on. So what I written here, this equation, the summation term is from n equal to minus infinity to plus infinity. So minus infinity to plus infinity. So many summation terms are there. But each summation is carried out. Each summation is carried out. I will write here. Each summation is carried out over n samples of x of n. Okay, therefore above equation means equation number 2 can be written as x of 2 pi by n into k is equal to, so each summation term carries how many n samples of x of n. So generally I will write the value of n varies from minus n to minus 1, x of n e to the power minus j 2 pi by n into kn. Next, this is also varies from next n samples. Next n samples means n equal to 0 to n minus 1, x of n e to the power minus j 2 pi by n into kn. Next summation term plus, next summation term is what? Summation n equal to the value of next value of n minus 1, that is n to 2n minus 1 x of n e to the power minus j 2 pi by n into kn plus so on up to where? Infinity, plus infinity. So the above individual summations can also be represented as, each individual summation terms I'm going to represent as in general x of 2 pi by n into k is equal to, so how many summation terms are there? Summation terms are minus infinity to plus infinity. So I will make use of one more index, L equal to minus infinity to plus infinity. So this index L indicates that how many summation terms are there. Next, each summation terms having length n samples, that one I am going to write it as n equal to minus ln, sorry, not minus, plus ln to ln plus n minus 1. Okay, simplify this one. What we are getting, if you take lower index is n equal to ln, upper index is n equal to ln plus n minus 1. If you take towards ln plus n minus 1, it is the upper index, upper limit, minus lower limit, that is ln. What we are getting, ln and ln get cancels, we are getting only what, n minus 1. So it becomes 0, upper limit becomes n minus 1. So generally speaking, each summation term contains n samples. So x of n e to the power minus j 2 pi by n into kn. Okay, now change the index of inner summation term from n equal to 0 to, I will write here, I am changing the index of inner summation term in order to avoid the confusion. The outer summation term as it is, I will write L equal to minus infinity plus infinity. I am going to change index of inner sum from n to n minus ln. So wherever n is there, write it as n minus ln. Otherwise, if you take ln towards LHS side, n minus ln equal to 0. Here n minus ln equal to 0 to n minus 1. So it becomes n equal to 0 to n minus 1. Okay, it means n is replaced by n minus l into capital N. So here n is there, that one I am writing n minus l into capital M e to the power minus j 2 pi by n into k. Once again n is there, so that one I am writing n minus l into n. For the simplification, summation l equal to minus infinity to plus infinity, summation n equal to 0 to n minus 1, x of n minus l into capital N. I will split the summation terms as e to the power minus j 2 pi by n into kn, first term. Next, multiplied by minus into minus, it becomes plus e to the power j 2 pi by n into k into l into n. So this n and this n get cancels. This one we are going to simplify as e to the power j 2 pi k into l, where k is the integer value, l is also integer value. So what will be the value of this one, where k is the integer value as well as l is the integer value? K may be any value, it may be 1 2 3, anything like this. L is also 1 2 3 like this. So what we're getting, simply by simplifying this one, we can write cos of 2 pi plus j sin of 2 pi. Cos of 2 pi is, we know that, 1. Sin of 2 pi is 0. So hence we are getting 1. Cos of even multiple of pi results in 1. That point we have to remember. Hence result is 1. So this one we can write as 1. Next, simplifying, what we are getting. So if you replace it by 1, so this equation we can write as x of 2 pi by n into k into, sorry, k is equal to summation l equal to minus infinity to plus infinity, summation n equal to 0 to n minus 1, x of n minus ln multiplied by e to the power minus j 2 pi by n into k into n. So let us rearrange the order of summation terms. The above equation becomes x of 2 pi by n into k is equal to, I will take this outside, summation n equal to 0 to n minus 1, summation l equal to minus infinity to plus infinity, x of n minus L into n multiplied by e to the power minus j 2 pi by n into kn. So observe this term. This term indicates that periodicity property. Periodicity property means the signal, discrete time signal x of n is going to repeat itself after every n samples. After every L samples. So this one I'm going to replace it as x of 2 pi by n into k is equal to summation n equal to 0 to n minus 1 xp of n. Xp of n nothing but xp of n indicates that it means xp of n is the periodic repetition of x of n with period of n samples, left with e to the power minus j 2 pi by n into kn. Okay, what this indicates? Equation number 3. This equation indicates that we sampled given sequence by n samples, where the value of k varies from k equal to 0, 1, 2, 3, so on n minus 1, and xp of n stands for what? It is the periodic repetition of x of n with period of n samples, that is summation L equal to minus infinity to plus infinity x of n minus L into n. Okay, so this is about frequency domain sampling. Before discussing reconstruction of signal, we will see one error, how the signals are going to get error, aliasing. Next we will discuss aliasing concept. So I'm going to consider one signal. Consider discrete time signal x of n. Let us consider discrete time signal x of n. If I it contains, here I consider one discrete time signal x of n. This signal contains L samples. If it contains L samples, then with the help of this case, we will discuss how we are going to get aliasing concept. Nothing but uh, the length of period. If you length of the period is indicated as n. If n is greater than L, what happens? If n is less than L, what happens? We will discuss. Okay, first I'm going to sketch one signal by considering let us take uh, let L equal to 4 samples. Here I have assumed that the length of the nothing but the discrete time signal contains 4 samples. So one example I will take, or this is 0th sample, first sample, second sample, first sample, second sample, third sample, fourth sample. Okay, this one is uh, signal x of n. Okay, here I consider discrete time signal x of n having 4 samples here of respective amplitude. Now with the help of this example, we'll discuss two cases, aliasing and no aliasing. First case number 1, if n is greater than L, what happens? If n is greater than L, I will take n equal to 6. Of course, L is how much? L is 4. If I take greater than L means the value should be taken more than 4, means because of that reason I have taken n equal to 6. 6 is greater than 4. What happens if length is, the period of the given signal is greater than the length of the sequence? Then what happens? So n indicates periodicity property, length of the period. So this signal x of n is going to repeat. It means what? The signal x of n is going to repeat after n samples. After n samples, already we discussed x of n minus L into n. N is the length of the period. Okay. If this length of the period is greater than number of samples present in this sequence, what happens? if it means the sequence x of n is going to repeat itself after every 6 samples. This is the given signal. If it is going to periodic signal, it has to repeat itself 0, first, second, third, fourth. But it has to repeat after every 6 samples. This is the fifth sample, first sample, second sample, third sample, fourth sample, fifth sample. It has to start from 6 samples. 6 samples means here. So the nature of this signal repeat itself from 6 sample. So on. Like this we are getting. Whether there is a overlap of sequence occurs here? No. There is no overlap of sequence. Hence there is no aliasing. Hence we can write no aliasing. If period length is greater than number of samples present in the given sequence, then there is no aliasing. This point we have to remember. Next we'll discuss when the sequence is going to get overlapping of sequences. It happens if and only if the period length is less than the number of samples present in the uh, given sequence. So second case, I will take case number 2. If n is less than L, n is less than L, what happens? So here I will assume n equal to 3, I will assume, because the length of L is the given sequence x of n contains 4 samples. N is less than L means I will take n equal to 3. So first sequence, as it is, I will sketch. Okay, this is 4, 3, 2, 1 amplitude. This is the sequence x of n. So as per this case, if the period length n is less than L, it means the sequence x of n, is going to repeat itself after every 3 samples. So first sample, second sample, third sample. So it will start repeating from here. 4. Next. So in this case, there is a overlap of 2 sequences. It is what? It is the sample of first sequence, and it is the sample of repetitive second cycle. This is the amplitude of first cycle. This is the amplitude of second cycle. So there is a overlap of 2 samples occurs. Hence, here we are getting aliasing. Here we are getting aliasing. So we can say that thus to avoid aliasing in time domain, the number of samples in the frequency spectrum must be greater than the number of samples in time domain sequence. I will repeat once again. We discussed 2 cases, aliasing as well as no aliasing. This is the aliasing case. To avoid aliasing in time domain, the number of samples in the frequency spectrum must be greater than number of samples in the time domain sequence. This is the case to avoid the aliasing. Okay.